Hello everyone, welcome to Raos Academy. Today we are going to discuss atmospheric circulation, very important for your UPSC prelims. Along with MCQs, we are going to discuss all the important topics in this atmospheric circulation. In atmospheric circulation, we are going to see global air circulation along with pressure belts and even local winds also. So let's start the session with MCQs, previous year questions, UPSC prelims 2024 question. Regarding atmospheric heat. Question: consider the following statements. Statement 1, the atmosphere is heated more by incoming solar radiation than by terrestrial radiation. 2, carbon dioxide and other greenhouse gases in the atmosphere are good absorbers of long wave radiation. They are asking about incoming solar radiation. Atmosphere is more heated by incoming solar radiation than terrestrial radiation. And which is correct? Both 1 and 2 are correct. And 2 explains 1. Option A. Option B. Both 1 and 2 are correct. But 2 does not explain 1. Option C. 1 is correct. 2 is incorrect. Option D. 1 is incorrect. 2 is correct. Here the answer is 1 is incorrect and 2 is correct, because atmosphere is more heated by terrestrial wave radiation, long wave radiation than incoming solar radiation. So the statement 1 is wrong. Statement 2 is correct. Yes, carbon dioxide and other greenhouse gases like water vapor, methane, all these are good absorbers of long wave radiation, terrestrial radiation. What? Infrared, IR, we have seen. Next question. So the answer is D. 1 is incorrect, 2 is correct. Next, which of the following absorbs terrestrial radiation? 1, carbon dioxide, 2, water vapor, 3, nitrogen. Option A, 1 only. Option B, 1 and 2. Option C, 2 and 3. Option D, 1, 2 and 3. They are asking about long wave radiation. All the gases present in the atmosphere are long wave, are greenhouse gases? No. The gas which absorbs long wave radiation are known as, or terrestrial radiation are known as, greenhouse gases. What are those gases? Carbon dioxide we have seen, water vapor. Nitrogen? No, nitrogen is not a greenhouse gas. So the answer is 1 and 2. Option B is the correct answer. Option B is the correct answer. Next, which of the following factors affect the amount of insolation received at a place? They are asking about the factors at a place. This you have to see. Insolation received. First, 1, angle of incidence of sun rays. 2, duration of sunshine. 3, transparency of atmosphere. 4, distance from the distance from the sun. A, 1 and 2. B, 1, 2 and 3. C, 1, 2, 3 and 4. D, 2 and 4. Most of the students, they think distance from the sun also affects the insolation received at a place. Here, no. Distance from the sun in a minor, in a minor amount, it will affect the seasons, not at a place. Seasonal variation you will see, but not received at a place, not at a particular place. Distance from the sea does not affect any place variation. So that you have to remember. Properly you have to learn the question. Properly you have to understand the meaning of the words. Whether they are asking seasons, whether they are asking about a particular place, whether they are asking about low latitudes or higher latitudes, they are asking about equator or poles, all those things you have to see properly in your exam. First, 1 is correct. Yes. Duration of sunshine. Yes. More daytime means more insolation. Transparency of atmosphere. Yes. Transparency of atmosphere also affect the amount of insolation, because when you take equator, Equator. At equator you will see most of the time vertical rays, means incoming solar radiation is more, but the absorption is more at subtropical highs, because at subtropical high, at subtropics, atmosphere is transparent. At equator you will see cloud formation, more cloud formation. If atmosphere is clear without clouds, you will see more incoming solar radiation, more absorption, more amount of insolation received at a place because of the transparency. So transparency of the atmosphere also affects the amount of insolation at a place. So 4 is not correct answer. The answer is B, 1, 2 and 3. Next, before going into global atmospheric circulation, we have seen factors affecting the velocity and direction of winds. At a glance, again we are going to see first main thing, pressure gradient force. Pressure gradient force, PGF, is pressure different force. If pressure difference is not there, the wind cannot move. Starting primary force responsible for the wind movement. Wind movement. Primary force. Wind moves from high pressure to low pressure. If high pressure and low pressure, the pressure difference is not there, wind cannot move, right? So factors affecting, first pressure gradient force, next Coriolis force. Coriolis force is also very important. It affects the direction. It affects the direction. It affects the direction. Next, frictional force. What affects velocity? Pressure gradient force affects the direction also. But Coriolis force does not affect the velocity, speed in a particular direction. It only affects direction. That you have to remember. Important point. Friction, yes, affects velocity. Here affects direction. Already I have explained all those things. Next, atmospheric circulation. Atmospheric circulation is very important. Why atmospheric circulation happens? We are going to see. First, in atmospheric circulation, we are going to see 3 types of circulations. First, primary circulation. Second, secondary circulation. 3, tertiary circulation. Under primary circulation is very important. Under primary circulation, trade winds, westerlies and polar easterlies come. They are known as planetary winds or permanent winds. In detail we are going to discuss. And under secondary circulation, you will get Indian Ocean dipole, monsoon, cyclone, anticyclones, means temperate cyclones, El Nino, La Nina, all these things comes under secondary. Under tertiary, we are going to learn local winds, thunderstorms, hailstorms, tornado, all these things. And in local winds, land breeze, sea breeze, everything we are going to see. These are the different types, different names of these local winds. So let's start the session with general circulation or primary circulation. General circulation, also known as primary circulation. General circulation is also known as primary circulation. Primary circulation. This global wind system, global circulation, general or global or primary circulation, very crucial for your weather and climate, because here you will see heat transfer. Heat transfer. It moves heat from low latitudes to high latitudes. Why? Because at low latitudes, at equator, you will see heat surplus. More incoming solar radiation. At poles, you will see less incoming solar radiation. Though Earth maintains equilibrium. It maintains heat budget, and we have seen distribution of heat from surplus areas to deficit areas. This general circulation, what it makes, it moves heat from surplus areas to deficit areas. If general circulation or a global circulation, air circulation is not there, you will see intense heat at equator and intense cooling at poles. So the heat distribution is very important, heat transfer. balancing Earth's temperature. Next, moisture transport. What it will do? It will transport the moisture. It carries moisture from oceans to continents. Carries moisture from oceans to continents, influencing the rainfall, cloud formation, and you will see hydrological cycle means water cycle. Why does general air circulation occur? Because of the main cause is uneven heating of Earth. Uneven heating of Earth. Because of this uneven heating of Earth, equatorial regions, you will see surplus, receive more solar energy. Already I have discussed. And additional influences, what it will influence? Earth's rotation. Because of this Coriolis effect, winds curve rather than they move, they curve. Next, gravity maintains atmospheric stability. So now what is? Like this, from equator it to move towards poles. Now we are going to see the movement and how air rises, sinks at different latitudes. We are going to see. First, how would winds move in this model? We have seen unequal heating, pressure gradient. Because of pressure gradient, wind moves from high pressure to low pressure. Wind moves from high pressure to low pressure. Yes? How unequal heating is related to pressure gradient? High temperature means low pressure, you will see. Low temperature means high pressure, you will see. Because hot air rises. Here you will see rising air. Cool air is denser, so it sinks. Clear? Because of this high pressure and low pressure, because of this temperature difference, you will see pressure gradient force. From here, a wind moves from here to here. Like that, you will see. Formation of single circulation cell. First in 1735, we have seen Hadley's unicellular circulation model. Now, we are going to see three cellular. First, we are going to discuss unicellular. Unicellular is a thermal circulation. Thermal circulation from 0 to 30 degrees he has discussed. Unlike pure, see, only he discussed about thermal circulation because of the temperature difference from high temperature regions to low temperature region. But now what we are following? We are following Ferrell's tricellular model of atmospheric circulation. We are following Ferrell's tricellular model of atmospheric circulation. Older, only temperature based circulation. This is very important for your exam. The modern three-cellular model explains circulation based on both temperature gradients and dynamic forces. Why? Because, see, we have three types of cells. Here, at subtropics also you will see high temperatures. But why air sinks? All those things we are going to explain. Means, temperature gradients along with dynamic forces, different pressure belts are formed. All the global, these three cells we are going to see. This model proposes that each hemisphere has three distinct air circulation. Means northern hemisphere 3 cells, southern hemisphere 3 cells with same names. With same names. What are those 3 cells? From 0 to 30, cell is known as Hadley cell. Here also, Hadley. From 30 to 60, Ferrell. 30 to 60, Ferrell cell. From 60 to 90, you will see polar. From 60 to 90. Here also, from 60 to 90, you will see polar. These three you have to remember: Hadley, Ferrell and polar. First remember 0 to 30, Hadley cell. 30 to 60, Ferrell cell. 60 to 90, polar cell. This you have to remember. First remember the names. Then we are going to see the circulation. First, Hadley cell 0 to 30. Here what happens at 0 degrees? Warm air rises. Here at 0 degrees what happens? This is 0 degrees. Here warm air rises. We are talking about troposphere. Everything in troposphere. All weather conditions where you will see. We are seeing all this global air circulation from troposphere, from surface of the earth to tropopause, from surface of the earth to tropopause. Now here this is the surface. Now here tropopause. Listen carefully, this is tropopause. Okay. Now here 0 degrees. Don't see here. I am drawing like this. Now this round turn like this. You are going to understand. Surface. Now this is 0 degrees. Here 30 degrees. Here 30 degrees. First we are going to see Hadley cell. What happens at 0 degrees? Warm air rises because more warm air rises. And at tropopause, what you will see? You will see divergence. Now, first you see scenario at equator. At equator, what happens? Warm air rises. And what happens here? When warm air rises, you will see low pressure. Low pressure. Now, warm air is rising. Here, you will see condensation, rainfall, everything. You will see here at equator zone. Cloud formation, rainfall, precipitation. After diverging, when this air move towards poles, because we are seeing heat transfer from equator, air is moving towards poles, right? Towards poles. In this journey, what happens? You will see radiative cooling. Because moisture is lost because of this rainfall and condensation, you will see moisture content is decreased and this warm moist air becomes dry as it moves towards pole side, and that dry air, it will sink at 30 degrees temperature because air is dense. Air is dense. From 0 to 30 degrees at here. When air is moving towards poles, because of radiative cooling, air sinks at 30 degrees. Air sinks at 30 degrees. Here density density increases. Here density is low. Air density is low, and here you will see divergence at tropopause, and as the density increases because of the gravity, what you will see? You will see the sinking effect at 30 degrees. This is not due to thermal effect. This is not due to thermal induce. This is because dynamic factor. Dynamic factor because this is the rising arm of Hadley cell. From 0 to 30, what cell we have seen? Hadley cell. 0 to 30. Now this is the rising arm. Here this is the sinking arm. Not because of the temperature, because of radiative cooling and upper air convergence, at tropopause you will see sinking air. You will see sinking air. That's why at subtropics you will see more deserts, and at those deserts, even though the temperature is high, you will see high pressure area. That's why we call that subtropics as subtropic highs. Subtropical high pressure zone. Why? Because of this sinking arm of Hadley cell. Here rising, moving towards, and here you will see sinking. At 30 degrees you will see sinking. At this 30 degrees latitudes you will see more deserts and dry air and sinking of air you will see. Though the temperatures are very high, clear skies with high temperatures, at high temperatures what you will see? Low pressure usually. But at subtropics you will see high pressure because of this sinking arm of Hadley cell, not thermal induced, because of dynamic factor. This reason they can ask in a statement. This reason they can ask in a statement. See, warm air rises at equator due to intense heating, reaching 8 to 12 kilometers in height. 8 to 12 kilometers in height means at tropopause. The air diverges towards pole at high altitudes. Some of this air descends near 30 to 35 degrees latitudes, forming the subtropical high pressure belt. Now we are going to discuss high pressure belt afterwards in detail. The descending air returns to the equator as a trade winds, forming a complete convective loop. This explains trade winds and why hot deserts are found near 30 degrees latitude. Very important how we are going to link Hadley cell global air circulation with trade winds and subtropical high pressure belts and even deserts. If you see the diagram, see upper air circulation, and this is the sinking air at 30 to 35 degrees. Now sinking air means what you will see? High pressure zone. High pressure means here at subtropics it is sinking. Here you will see subtropical high pressure belt. Subtropical high pressure belt. Here what you will see? Here you will see equatorial low pressure belt. Equatorial low pressure belt. Now two pressure belts we have seen, and this air movement due to trade winds, permanent winds, again this air move towards equator. Wind moves on the surface from high pressure to low pressure. Yes, high pressure to low pressure on the earth's surface. Wind moves from high pressure to low pressure in the form of trade winds. In the form of trade winds. This is how you have to interlink trade winds, subtropical high pressure, equatorial low pressure. A convective loop like this. Rising, sinking. 0 degrees rising, 30 degrees sinking. That you have to remember. Now, Hadley cell clear, same in northern hemisphere and southern hemisphere, same phenomena. At Ferrel cell, 30 to 60 degrees. What happens at Ferrel cell? We are going to see. Here, westerlies blow from subtropical high pressure belt to the subpolar low pressure. Because of these westerlies, warm westerlies rise near 60 to 65 degrees. Here also, see what you have to remember, complete Ferrel cell is due to dynamic factors, not thermal, dynamic factors. We have two types of factors. One is thermal. Thermal you will see at equator and poles. Now when wind is moving from 0 to 90 degrees towards poles, in between you will see dynamic factors. Because here at tropopause, because of the radiative cooling, here you will see sinking. But here what happens? Rising you will see. At 60 degrees compared to this, here you will see more temperature at temperate zone. So here you will see low pressure zone. Because of this low pressure, here you will see rising air, and here you will see temperate cyclones at 60 degrees. And this 60 degrees, because here you will see westerlies, warm southwesterlies you will see. Warm, because of this warm westerlies, here you will see in temperate zones moist warm air rising, low pressure. And this at tropopause, what you will see? Divergence. And this divergence you will see convergence. This arm from 60 degrees, because of the low pressure air rises, and here you will see sinking of air at Ferrel cell 30 degrees. See, from two sides we have seen convergence. Here at 60 degrees rising, at 0 degrees rising. Here sinking, and here in north also you will see sinking. Clear? Sinking. First, what you have to remember? 0 degrees rising. Now this rising sink at 30 degrees. Now again at 60 degrees rise. Now this rise you will see sinking at 30 degrees. And at 90 degrees also you will see sinking. Clear? Now here you will see, because of the dynamic factors you will see sinking. This 0 degrees and this 90 degrees, these two are related to thermal factors because of temperature. Now we have seen these three cells. In these three cells we are going to discuss pressure belts and even trade winds also. Pressure belts. From this to this, from starting of this cell and ending of this cell, we are going to see different pressure belt zone. And from on the surface, from ferrule to hardly, from ferrule to polar and polar to ferrule, wind movement. We are going to see permanent winds. See, cold air from the polar high pressure zone move towards 60 to 65 degrees as polar easterlies. We are going to see the easterlies and westerlies. Rising air at subpolar low pressure zone diverges at high latitudes. We have seen divergence. And some of this air move towards poles and descends at pole side. Here you will see descending of air, reinforcing the polar high pressure. First, low pressure, high pressure, low pressure, high pressure. This is at 90 degrees high pressure, 0 degrees low pressure. Like this you can remember. Now, pressure belts of earth. Pressure belts of earth are continuous zones of high and low atmospheric pressure that shape the planet's wind system. Because of these pressure zones, wind moves from high pressure zone to low pressure zone. High pressure zone to low pressure zone. We are having four pressure belts: the equatorial low pressure belt, the subtropic high pressure belt, the subpolar low pressure belt, and the polar high pressure belts. 4 in northern hemisphere and 4 in southern hemisphere with same names. Now we are going to see equatorial low pressure belt. Now we have seen Earth showing alternative sequence of low and high pressure. At equator low pressure, next 30 high pressure, next 60 low, and again at 90 high pressure. We have seen. So first, equatorial low pressure. Equator what happens? Shines almost here. As a result, what happens? Air rises. We have seen in global air circulation. This pressure belt extends from equator to 10 degrees in north and 10 degrees in south. Due to excessive horizontal movement of air is absent. Strong vertical rising you will see. Horizontal air is absent. Only convectional currents are very strong. This statement you have to remember, very important. Okay, because of this absence of horizontal air. Therefore, this belt is known as doldrums, because doldrums means the zone of calm due to virtual absence of surface. Because of the virtual absence of surface, the zone is, most of the students they strong movement of horizontal air movement. No, horizontal air movement is almost absent, but vertical convectional movement is very strong. These are the regions of convergence, because here the wind flows from subtropical high pressure. Now this is here equatorial low pressure. This is subtropical high pressure. Wind moves from subtropical high pressure to low pressure, and here you will see convergence at surface and divergence at upper air surface. That's why this belt is known as intertropical convergence zone. Intertropical convergence zone. ITC is very important for your Indian monsoon class. Next, subtropical high pressure belts. Subtropical high pressure. About around 35 degrees of latitudes in both the hemispheres, northern hemisphere and southern hemisphere. What happens to the air? This is rising air descends here. The existence of these pressure belts is due to the fact uprising air we have seen at equatorial region deflected towards poles. What happens? Air in atmosphere, the air becomes cold and heavy, and here it descends in this regions. Calm conditions you will see in olden days, these are also known as horse latitudes. Why? Because in olden days what happens with cargo of horses passing through these latitudes, they used to see difficulty in sailing under calm conditions. Under calm conditions, if winds are not strong, moving of the boat or a ship becomes hard. So they used to throw the horses in the sea in order to make the vessels lighter. That's why these latitudes are known as horse latitudes. This you have to remember. High pressure. Here you will see deserts. Next. Subpolar low pressure belt. Subpolar low pressure belt extends from 45 degrees and the Arctic Circle, northern hemisphere, and between 45 and Antarctic Circle in the southern hemisphere. This you have to remember. Subpolar low pressure. Subpolar low pressure. Low pressure you have to remember. Don't think polar means always high pressure. Subpolar low pressure. See, two subpolars and subtropical, they are due to dynamic factors, and polar and equator are due to thermal. They are known as north subpolar low and south subpolar low pressure belts. Here what happens? Winds coming from the subtropical and the polar high pressure. Subtropical high pressure, polar high pressure converge here. Sorry. Now winds coming from this side and from this side. What happens? Here they converge at warm easterlies, and you will see rising. And here it creates low pressure conditions. And this zone of convergence here is known as polar front. Because of this polar front, here you will see temperate cyclones. In detail we are going to see in cyclones chapter. Next, polar high pressure belt. In polar region, sun never shines vertically. This you have to remember, very important. Sun never shines vertically. Sun rays are always slanting here. And what you will see here, you will see low temperatures. Because of low temperature, you will see dry air, cold and dry air. Density also very high, and because of this density increases, here you will see high pressure, polar high pressure. Okay. In northern hemisphere, it is called as north polar high pressure belt, and while in south polar high pressure belt. These pressure belts you have to link with Hadley, Ferrel and polar cells. For example, if I ask see, this is equatorial low pressure, and from here Hadley cell starts. Yes, and at here, and from here you will see Ferrel cell, and from here you will see polar cell. So, horse latitudes, subtropical high pressure zone is at, if I say subtropical high pressure zone is at descending arm of Hadley cell and ascending, and one arm of Ferrel cell and one arm of Hadley cell. It is true or false? Yes, it is true. These cells you have to remember, you have to interlink with pressure zones. Because of these cells only you will see the pressure zones. Low pressure, high pressure, low pressure and high pressure. This sequence you have to remember: low pressure, high pressure, low pressure and high pressure. This is at 0 degrees, this is at 30 degrees, this is at 60 degrees, this is at 90 degrees. Here what happens? At 0 degrees, because of low pressure and strong convection and continuous formation of clouds, what you will see? Here you will see rainforest. Here you will see rainforest. Rainforest formation. At 30 degrees, descending air, dry air, and you will see deserts. Subtropical. Here you will see temperate cyclones. Here you will see temperate cyclones at 60 degrees. At 90 degrees you will see tundra zone. Means with these pressure belts, with these global air circulation, we have to interlink with the landforms and even natural vegetation. Okay? They can ask in a statement, for example, in statement 1, they can ask at 0 degrees we see rainforest. In statement 2, they can give the explanation: because of low pressure zone, because of high convectional currents, or because of strong horizontal air movement. So, the explanation will be wrong. Like that you have to remember. No strong horizontal air movement, you will see strong convectional currents. Because of that strong convectional currents, strong cloud formation, you will see rainforest. And because of the strong cloud formation, throughout the year you will see rainfall. Because of that rainfall, you will see rainforest. This is how you have to interlink climatology with natural vegetation. And we are going to interlink this climatology with oceanography also, and even with our Indian monsoon. So, tomorrow we are going to discuss jet streams and along with shifting of pressure belts and even local winds also. Thanks for watching.